without further ado, let me introduce the speakers of today. Ege, have you started the registration? Because I didn't get the notification.
You can, the recording has started, yeah.
Okay, I'm sorry, I didn't get the notification. So, okay, let me introduce the speakers today. We have two figures well known in the community, in the Web of Things landscape. We have today with us Ege Korkan, which is the co-chair together with me of the community group, and is a research scientist at CIMIS AG. He worked for quite a lot of time in Web of Things topics in the working group and also during his PhD. And together with him, there's Fady Salama, which is a PhD candidate at TUM Institute in Germany. His works is also a very well-known figure in the Web of Things working group and the community group. He helped us with the testing task force, and his work centers around exploring how what can be used in industrial application with some additions. So, Fady, Ege, the floor is yours.
All right. So today we will be talking about digital twins, more specifically about interactable digital twins. And we will focus on the robots, and the way we will accomplish this is, of course, with the Web of Things, and that's why we're here. And as Christiane has introduced, so it will be done by me and Fady, and we have a long ongoing collaboration with the university in Munich, and that's also like a joint work between Siemens and TUM. Yeah, so I'll go straight into the topic, and I'll first start with device connectivity. It's something that is sometimes ambiguous, but actually what we really want to focus on is how we interact with the devices. Yeah, there are different patterns, but in the end, what we want to focus on is the control logic or mashups or the application logic, business logic, however you call it. And there are different patterns, like I said, so we could be in a factory or building, or yeah, like in a smart home environment. And we could interact directly with the devices to move the robots, to read the temperature, or turn on and turn off the lights. And there could be a gateway in the middle, but in the end, what the control logic cares about is the logic itself, right? And we can do it also differently. Maybe there are different rules on the network, so we cannot just be interacting directly. So we need maybe some cloud access where we are still controlling those devices through this cloud endpoint. And in that case, we are starting to see those virtual devices or virtual assets. And maybe at that point, we start discussing a bit about digital twins. But this is still quite simplistic. So with digital twins, we are expecting to see something a bit more than just translating requests and so on. And that's why today we are actually looking into simulation software. And I think everybody knows about simulation software in general, but we want to highlight some of the common aspects and the type of simulation software we are focusing on. Yeah, so simulations, and nowadays they are sometimes wrapped as digital twins. And yeah, this is like a big discussion that I won't go into, but in the end, with simulations, what we want to do is predict the behavior or the outcome of a real world or system. So all of the weather reports we are seeing is basically result of such simulations. Whether the weather reports are accurate or not, it depends on where you live, but they are also, maybe simulations. And in all of these systems, we have the model system, and we have the run simulation, and we then get the results, to compare with real life. And very importantly, me, Fady, or anybody in my immediate vicinity is a simulation expert. So we do not want to reinvent how simulations are done, nor do we have the knowledge. But of course, Siemens, among many others, have very sophisticated simulation software, and there's no way we want to reinvent such stuff. So with such software, for example, on the right-hand side, you can simulate how a factory works, and you can plan ahead. And actually, there are two types that we have seen. So on one side, they are more or less real-time or can be made real-time. if you think of it, even a state machine simulation is a simulation, and that is very typically something that happens in milliseconds. So yeah, you don't even see the simulation running. Or if you think of a wind turbine, of course, that is something much more complicated, where they are generally much slower than real time. So if you want to look at the turbulences and so on in a wind turbine. And generally, these are software running in your computer. Very typically, it's a desktop application. And generally, you can also use like high performance clusters so that you can get your results much faster. And today, we will focus on the first one, because at least for us, the second category was not suitable for interactable digital twins, since when you interact with the real world, in order to get your new simulation, you need too much time. So for us, it's more for design stage optimizations. So if you want to design your wind turbine, you may want to use something with much more precision, so you can really see the real life. Right. So then more specifically, today we are looking at this simulation software. It's called CoppeliaSim. It's a commercial software, but has free and educational licenses. So if you are part of a university, you can use it for free. And we asked ourselves one question. So we know that we have thing models in the Web of Things, so that if I'm building a device that will be deployed, I can have thing models. And then once they are deployed, we get the thing descriptions. So in a way, thing model is something that the manufacturer provides. And what about the same for the robot models? So on the left-hand side, you're seeing that there are actually some robots sort of in the inventory, like from KUKA. And actually, there is a similar concept, and it's called the URDF, Universal Robot Description Format. It has nothing to do with the semantic web RDF format, but it is also an XML file format. And it's very simplistic in nature. It's basically just for describing robots, so that you can describe the hierarchy of links and joints. Of course, with this, you can describe the geometry and physical attributes, also like inertia, so that you can adjust how fast the robot moves. And you can then wrap this sort of like rectangles in like realistic STLs, so like the 3D CAD files, so that it really looks like the real robot. And then in the end, you can exchange the robot models. And it's actually already happening. So on GitHub, there are companies like well-known in the robotics space sharing their URDF files. That means that you can take these and use them in different simulation software, a bit like taking a thing model or a thing description and using it in other software. So it has this nice decoupling effect. And then with this, we basically built robot, and I will actually go straight to demo. So we will show it for robots, but of course we can extend it for other things. So as I said, I'll go straight to demo. And what we will see will be on one side, the real-time video stream of a lab setup in TU Munich that is exposed to the public internet, but behind a secure proxy. And we have a digital twin of it working in my laptop with the CoppeliaSim. And then we will show some code that will be executed on both systems. Okay, so this is what it is now before we started anything, just to see. So on the left-hand side is the real-time camera feed. So you're seeing the time incrementing here. And on the right-hand side is the simulated instance. So the left-hand side is basically this table specifically, but we have some other stuff in this room, like another table, another robot. So basically, I will be focusing on this side. And basically, what I have on here is the code, which is, by the way, open source. So we will show that in a second. So I will start one thing that is basically interfacing with the simulation environment. And then I will start our code. So now let's go back to the here. So I will need to zoom again. And you are now seeing the simulation and the real life behaving the same way. So as you can see, the robot is, both robots are moving sort of the same. So if you look like this, yeah, so they both move to the right, and now they will both move to the left. Of course, the speeds are not exactly the same, and the movements might not be exactly the same, but that's sort of not the point. And then in a second, I will show exactly what code is working behind the scenes. And if you're familiar with node-wot, you will see that it's not so different. It's not so foreign. Right, so I will come to this in a second, but just to show that we have some basically usual imports of the library, and then we basically have the thing descriptions of the virtual devices and the real devices. And what is actually happening, so I'll then skip here, is this very boring code, and we are quite happy that it's very boring, because actually, thanks to thing description, you are able to abstract yourself from all the like inner workings and like what kind of requests you need to generate, and you can really focus on your control logic, which we're seeing here. And as you can see, we are basically calling the same action on the two entities. So this is the virtual robot, and this is the real robot. Similarly, we have the conveyor belts here, and we are always calling the same action. But of course, this one, the virtual one, is going into my laptop, so using localhost and so on. And this one is using the secure proxy, which means I need to provide credentials and so on in order to recall this. And if you look into their thing descriptions, actually, you will see it. So in the real one, we are seeing the domain names, and on the virtual ones, as expected, we will be seeing the localhost. And the best thing is actually for the local ones, we can even change the protocols, and this code that I've just shown will not change. So actually, you don't even have to know what protocol is being used, since we are able to abstract it away with the thing description. Right, so with this, I will stop the first demo, and I will give it to Fady, who will explain to us how it's really working behind the scenes.
Hi everyone, Fady, and I will try now to explain how this framework has been developed in the university. So the idea was we start only using the URDF. So you have the robots, you have its URDF. We wanted to reach a level of autonomy in which basically you just start with the URDF, and the most of the work that is being for generating the robot simulation and its interactions and the server that you communicate with happens autonomously without or with very minimal human intervention. So you just start by importing the URDF in your simulator, which in this case is CoppeliaSim, and then we do some generation for the workspace. Basically, the workspace means the place where the robot can move. And we will see how this is happening and why do we do this. Then we enhance the TD using some information that we gathered with the workspace to make sure that we can describe the robot effectively. And then now that you have a server and that can communicate with the simulator, you can now have some user interact with the simulated robots, and it should work fine. So that's generally just the big overview, but let's look at exactly how a developer would normally use such a simulation. So the first thing would be he would probably get so if you have a robot, the developer would probably get its thing model, which is basically its interface, all the interfaces that described from the manufacturer. Then possibly also the URDF with the STL files from the manufacturer. And then here we use a simulation software, here in our case CoppeliaSim, to do the simulation. Then there needs to be a bridge between how the thing model looks, so basically how the interfaces of the device network interfaces look, and the simulation logic that happens via the code. So we need a bridge that does that basically translation. And then you start a program that would then generate the TD, so the instance, the thing description that will describe this instance of the robot on the simulation, and then the simulation is interactable. And the good thing with our approach, all of these steps 1, 2, 3, and 5, they can happen with no development effort at all. So the developer does not need to do anything. So these come from the manufacturer anyway. This is a simulation software that is from the outside. And this, we'll see node-wot will help us with that. The only thing that the developer needs to do is to write the small snippets of code that will do the interaction with the simulation. So when doing an interaction, for example, what should happen in the simulation. And the nice thing is that because the interfaces are the same, so you have the same thing model, and the same thing model would describe the real robot and the simulation of it, you basically get the same control logic, and your control logic stays the same, even if the two, even if you have a different, like a physical robot and a virtual robot. So how do we do this? So we have a thing model, which describes the interaction handling that that the robot has, what kind of interactions the robot provides, and these interaction handles can influence the simulation. So that's one block. Using that thing model, we can instantiate a server or a thing, and using that, and of course also its TD. Then there's a network communication happening between the Web of Things side of things, so that's your Web of Things stack, and the simulation stack. Here is the simulation instance or the scene. And then the control logic does not interact with the simulation itself. The control logic is interacting with the server that is describing the robot or simulation of the robot. And indirectly, through this communication channel, it influences what is happening in the simulation scene. So in essence, the control logic that we are writing is not directly communicating with the simulation. It's doing it indirectly through the Web of Things stack that we have. And all of the instantiation that's happening here is happening using Eclipse node-wot. So for those who do not know about what node-wot is, it's basically a scripting API or an implementation of the scripting API described by the Web of Things standard. And it basically makes instantiating a server or even a client in the Web of Things context very easy, and abstracts away from the protocols and giving you access to basically the control logic without the need to really think about which protocol you are going to use or how the protocols influence your logic. So your logic is just based on what kind of interactions you want to do. So that's how it generally looks like. And of course, the simulation software can change. Even the scripting API stack can change, but that this is the framework itself and how the concept looks like. In our case, we have the simulation software as CoppeliaSim, simply because it has a very good facility for like generating robots from URDF, as well as a good remote API that can be used from the outside by any other stack. Then here we have the Web of Things, node-wot, and for each robot, we instantiate a new server or a new thing that can then be interacted with, and the communication between that server and CoppeliaSim is happening via WebSockets. And yeah. And we can look at robot. So the whole framework is open source. You can look at it yourself. You can try it yourself. And you can even contribute to it if you want. And we can also have a look at the conveyor belt example and how the conveyor belts in our simulation looks like. So basically, you can see here what we do is very streamlined. The first thing we have is a conveyor belt TM, a thing model that describes what interactions we expect the conveyor belt to have. In our case, moving it forward and backwards and stopping it. Then we introduce a class, virtual conveyor belt, which basically allows us to be able to instantiate multiple instances of that conveyor belt. You can see here for starting a thing, we look at the conveyor belts, and then here you can see in what produce we are doing what we normally do in node-wot, which is basically produce a new instance or thing, and we program very normally. And here, for example, in a thing set action handler, we tell exactly what should we do when we get an interaction request start belt backwards, and only that part in line 38 awaits this conveyor belt speed. This is the only part where it is basically developer work, where the developer, he or she needs to say what should happen in the simulation. So for example, changing the speed of the conveyor belt to move it forward or backwards. Then after we finish all our describing all our interactions and what they do in the simulation, we just expose the thing, and then it is accessible and can be interacted with.
Yeah, so at the same time, we did a side contribution, so to say, since we realized that using robots in the Web of Things is not so easy. So actually, there is a limitation. So robots are, in a way, very special devices. So what you see here is a robot suspended in space, which never happens. They are always mounted on something, and they have stuff around them, like we saw with the conveyor belts. So we can actually not describe it perfectly. So we cannot basically describe the available workspace of the robots. And yeah, it's actually much worse if there are other objects, other robots around it. And so for that, we took an approach where we look at the scene. So that's what we saw before. And we do different movements in order to calculate where we can really move. So we do this in the virtual space, meaning that, yeah, of course, you cannot hit the conveyor belt since the simulation knows to calculate such intersections and so on. And in the end, we are able to build a a workspace. So of course, this is a very complex representation. Like it's like a half donut, but it's not empty in the middle neither, and it's not circular. So yeah, mathematically it's difficult, but you can actually give the STL file as like an action input description if there are such consumers, but this is very unlikely. And so for those things, you have to actually keep the simulation in the loop in order to really be able to check whether those inputs are possible. Of course, you can also just do trial and error, but for dynamic systems, that will not be so possible since, whatever you tried before may not work when you really deploy it. Yeah, so in the end, what we really enable, so as we said, it's one side is the dry running or simulation in the loop. And what you can do is, like move a robot to a certain position. And then if it is, colliding, then maybe you should not move to that position exactly. So you can now like switch to something else. And when you know that you can move there, on possibly if your whole control logic works, then you can deploy it without changing your control logic, so that you can move the real robot the same way. And since we've shown already, so the same affordances means the same logic, so you don't need to change much in your code. And you can, of course, very easily compare the reality with the plan. So maybe the robot hit something on the way, so what you're seeing in real life shouldn't match what is supposed to happen. So there you can really easily identify discrepancies. And of course, maybe more interesting is that you can add such connectivity to your simulation software, since this basically does it in an interoperable way for everyone, and which will be also standardized. And that way, your simulation software could become a digital twin application that is usable over the network. So in the end, this is not like a silver bullet that will work everywhere. I mean, the code itself, there are, of course, the code to bridge it to CoppeliaSim in the specific case, but I hope that you can be inspired from this and implement it in your own way with maybe other simulation software. But I hope this gives motivation for it. Right, so with this, I have one more thing, and hopefully it will work. So we leave this to the end, since there are more chances of things going wrong. So as you've seen in the previous demo, there were more things around us, but we didn't like interact with all of them. Yeah, so since it's similar to the previous one, but there are many more sequential interactions with the robots, and so there's more risk of something going wrong. Yeah, so if we get a failure, we'll just cut it in the video and not put it on YouTube.